Chapter 4 Aerodynamic Factors. Introduction. Several factors affect aircraft performance, including the atmosphere, aerodynamics, and aircraft icing. Pilots need an understanding of these factors for a sound basis for prediction of aircraft response to control inputs, especially with regard to instrument approaches, while holding, and when operating at reduced airspeed in instrument meteorological conditions, IMC. Although these factors are important to the pilot flying visual flight rules as VFR, they must be even more thoroughly understood by the pilot operating under instrument flight rules, IFR. Instrument pilots rely strictly on instrument indications to precisely control the aircraft, therefore, they must have a solid understanding of basic aerodynamic principles in order to make accurate judgments regarding aircraft control inputs. End of page 4-1. The wing. To understand aerodynamic forces, a pilot needs to understand basic terminology associated with airfoils. Figure 4.1 illustrates a typical airfoil. The chord line is the straight line intersecting the leading and trailing edges of the airfoil, and the term chord refers to the chord line longitudinal length as viewed from the side. The mean camber is a line located halfway between the upper and lower surfaces. Viewing the wing edgewise, the mean camber connects with the chord line at each end. The mean camber is important because it assists in determining aerodynamic qualities of an airfoil. The measurement of the maximum camber, inclusive of both the displacement of the mean camber line and its linear measurement from the end of the chord line, provide properties useful in evaluating airfoils. Review of basic aerodynamics. The instrument pilot must understand the relationship and differences between several factors that affect the performance of an aircraft in flight. Also, it is crucial to understand how the aircraft reacts to various control and power changes, because the environment in which instrument pilots fly has inherent hazards not found in visual flying. The basis for this understanding is found in the four forces acting on an aircraft and Newton's three laws of motion. Relative wind is the direction of the airflow with respect to an airfoil. Angle of attack, AOA, is the acute angle measured between the relative wind, or flight path, and the chord of the airfoil. Figure 4.2, flight path is the course or track along which the aircraft is flying or is intended to be flown. The four forces. The four basic forces, figure 4.3, acting upon an aircraft in flight are lift, weight, thrust, and drag. Lift. Lift is a component of the total aerodynamic force on an airfoil and acts perpendicular to the relative wind. Relative wind is the direction of the airflow with respect to an airfoil. This force acts straight up from the average, called mean, center of pressure, CP, which is called the center of lift. It should be noted that it is a point along the chord line of an airfoil through which all aerodynamic forces are considered to act. The magnitude of lift varies proportionally with speed, air density, shape and size of the airfoil, and AOA. During straight and level flight, lift and weight are equal. End of page 4-2. Weight. Weight is the force exerted by an aircraft from the pull of gravity. It acts on an aircraft through its center of gravity, CG, and is straight down. This should not be confused with the center of lift, which can be significantly different from the CG. As an aircraft is descending, weight is greater than lift. Thrust. Thrust is the forward force produced by the power plant/propeller or rotor. It opposes or overcomes the force of drag. As a general rule, it acts parallel to the longitudinal axis. Drag. Drag is the net aerodynamic force parallel to the relative wind and is generally a sum of two components, induced drag and parasite drag. Induced drag. Induced drag is caused from the creation of lift and increases with AOA. Therefore, if the wing is not producing lift, induced drag is zero. Conversely, induced drag decreases with airspeed. Parasite drag. Parasite drag is all drag not caused from the production of lift. Parasite drag is created by displacement of air by the aircraft, turbulence generated by the airfoil, and the hindrance of airflow as it passes over the surface of the aircraft or components. All of these forces create drag not from the production of lift, but the movement of an object through an air mass. Parasite drag increases with speed and includes skin friction drag, interference drag, and form drag. Skin friction drag. Covering the entire wetted surface of the aircraft is a thin layer of air called a boundary layer. The air molecules on the surface have zero velocity in relation to the surface. However, the layer just above moves over the stagnant molecules below because it is pulled along by a third layer close to the free stream of air. The velocities of the layers increase as the distance from the surface increases until free stream velocity is reached, but all are affected by the free stream. The distance, total, between the skin surface and where free stream velocity is reached is called the boundary layer. At subsonic levels, the cumulative layers are about the thickness of a playing card, yet their motion sliding over one another creates a drag force. This force retards motion due to the viscosity of the air and is called skin friction drag. Because skin friction drag is related to a large surface area, its effect on smaller aircraft is small versus large transport aircraft where skin friction drag may be considerable. Interference drag. Interference drag is generated by the collision of airstreams creating eddy currents, turbulence, or restrictions to smooth flow. For instance, the airflow around a fuselage and around the wing meet at some point, usually near the wing's root. These airflows interfere with each other, causing a greater drag than the individual values. This is often the case when external items are placed on an aircraft. That is, the drag of each item individually, added to that of the aircraft, are less than that of the two items when allowed to interfere with one another. End of page 4-3. Form drag. Form drag is the drag created because of the shape of a component or the aircraft. If one were to place a circular disc in an airstream, the pressure on both the top and bottom would be equal. However, the airflow starts to break down as the air flows around the back of the disc. This creates turbulence and hence a lower pressure results. Because the total pressure is affected by this reduced pressure, it creates a drag. Newer aircraft are generally made with consideration to this by fairing parts along the fuselage teardrop so that turbulence and form drag is reduced. Total lift must overcome the total weight of the aircraft, which is comprised of the actual weight and the taildown force used to control the aircraft's pitch attitude. Thrust must overcome total drag in order to provide forward speed with which to produce lift. Understanding how the aircraft's relationship between these elements and the environment provide proper interpretation of the aircraft's instruments. Newton's first law, the law of inertia. Newton's first law of motion is the law of inertia. It states that a body at rest will remain at rest, and a body in motion will remain in motion at the same speed and in the same direction until affected by an outside force. The force with which a body offers resistance to change is called the force of inertia. Two outside forces are always present on an aircraft in flight: gravity and drag. The pilot uses pitch and thrust controls to counter or change these forces to maintain the desired flight path. If a pilot reduces power while in straight-hand level flight, the aircraft will slow due to drag. However, as the aircraft slows, there is a reduction of lift, which causes the aircraft to begin a descent due to gravity. Figure 4, Newton's second law, the law of momentum. Newton's second law of motion is the law of momentum, which states that a body will accelerate in the same direction as the force acting upon that body, and the acceleration will be directly proportional to the net force and inversely proportional to the mass of the body. Acceleration refers either to an increase or decrease in velocity, although deceleration is commonly used to indicate a decrease. This law governs the aircraft's ability to change flight path and speed, which are controlled by attitude, both pitch and bank, and thrust inputs. Speeding up, slowing down, entering climbs or descents, and turning are examples of accelerations that the pilot controls in everyday flight. Figure 4.5, Newton's third law, the law of reaction. Newton's third law of motion is the law of reaction, which states that for every action there is an equal and opposite reaction. As shown in Figure 4.6, the action of the jet engine's thrust or the pull of the propeller lead to the reaction of the aircraft's forward motion. This law is also responsible for a portion of the lift that is produced by a wing, from the downward deflection of the airflow around it. This downward force of the relative wind results in an equal but opposite, upward, lifting force created by the airflow over the wing. Figure 4.6, Atmosphere. The atmosphere is the envelope of air which surrounds the Earth. A given volume of dry air contains about 78% nitrogen, 21% oxygen, and about 1% other gases such as argon, carbon dioxide, and others to a lesser degree. End of page 4-4. Although seemingly light, air does have weight, and a 1 square inch column of the atmosphere at sea level weighs approximately 14.7 pounds. About 1/2 of the air by weight is within the first 18,000 feet. The remainder of the air is spread over a vertical distance in excess of 1,000 miles. Air density is a result of the relationship between temperature and pressure. Air density is inversely related to temperature and directly related to pressure. For a constant pressure to be maintained as temperature increases, density must decrease, and vice versa. For a constant temperature to be maintained as pressure increases, density must increase, and vice versa. These relationships provide a basis for understanding instrument indications and aircraft performance. Layers of the atmosphere. There are several layers to the atmosphere, with the troposphere being closest to the Earth's surface, extending to about 60,000 feet at the equator. Following is the stratosphere, mesosphere, ionosphere, thermosphere, and finally the exosphere. The tropopause is the thin layer between the troposphere and the stratosphere. It varies in both thickness and altitude, but is generally defined where the standard lapse, generally accepted at 2 degrees Celsius per 1,000 feet, decreases significantly, usually down to 1 degree Celsius or less. International Standard Atmosphere, ISA. The International Civil Aviation Organization, ICAO, established the ICAO Standard Atmosphere as a way of creating an international standard for reference and performance computations. Instrument indications and aircraft performance specifications are derived using this standard as a reference. Because the standard atmosphere is a derived set of conditions that rarely exist in reality, pilots need to understand how deviations from the standard affect both instrument indications and aircraft performance. In the standard atmosphere, sea level pressure is 29.92 inches of mercury, Hg, and the temperature is 15 degrees Celsius 59 degrees Fahrenheit. The standard lapse rate for pressure is approximately a 1 Hg decrease per 1,000 feet increase in altitude. The standard lapse rate for temperature is a 2 degrees Celsius 3.6 degrees Fahrenheit decrease per 1,000 feet increase, up to the top of the stratosphere. Since all aircraft performance is compared and evaluated in the environment of the standard atmosphere, all aircraft performance instrumentation is calibrated for the standard atmosphere. Because the actual operating conditions rarely, if ever, fit the standard atmosphere, certain corrections must apply to the instrumentation and aircraft performance. For instance, at 10,000 ISA predicts that the air pressure should be 19.92 Hg, 29.92 Hg, 10 Hg equals 19.92 Hg, and the outside temperature at -5 degrees Celsius, 15 to 20 degrees Celsius. If the temperature or the pressure is different than the International Standard Atmosphere, ISA, prediction and adjustment must be made to performance predictions and various instrument indications. Pressure altitude. Pressure altitude is the height above the standard datum plane, SDP. The aircraft altimeter is essentially a sensitive barometer calibrated to indicate altitude in the standard atmosphere. If the altimeter is set for 29.92 Hg SDP, the altitude indicated is the pressure altitude, the altitude in the standard atmosphere corresponding to the sensed pressure. The SDP is a theoretical level where the pressure of the atmosphere is 29.92 Hg and the weight of air is 14.7 psi. As atmospheric pressure changes, the SDP may be below, at, or above sea level. Pressure altitude is important as a basis for determining aircraft performance, as well as for assigning flight levels to aircraft operating at or above 18,000 feet. The pressure altitude can be determined by either of two methods: 1, by setting the barometric scale of the altimeter to 29.92 Hg and reading the indicated altitude, or 2, by applying a correction factor to the indicated altitude according to the reported altimeter setting. Density altitude. Density altitude is pressure altitude corrected for non-standard temperature. As the density of the air increases, lower density altitude, aircraft performance increases. Conversely, as air density decreases, higher density altitude, aircraft performance decreases. A decrease in air density means a high density altitude, an increase in air density means a lower density altitude. Density altitude is used in calculating aircraft performance. Under standard atmospheric conditions, air at each level in the atmosphere has a specific density. Under standard conditions, pressure altitude and density altitude identify the same level. Density altitude, then, is the vertical distance above sea level in the standard atmosphere at which a given density is to be found. It can be computed using a Koch chart or a flight computer with a density altitude function. Figure 4.7, end of page 4 to 5. If a chart is not available, the density altitude can be estimated by adding 120 feet for every degree Celsius above the ISA. For example, at 3,000 feet PA, the ISA prediction is 9 degrees Celsius, 15 degrees Celsius, lapse rate of 2 degrees Celsius per 1,000 feet x3 is equal to 6 degrees C. However, if the actual temperature is 20 degrees Celsius, 11 degrees Celsius more than that predicted by ISA, then the difference of 11 degrees Celsius is multiplied by 120 feet equaling 1,320. Adding this figure to the original 3,000 feet provides a density altitude of 4,320 feet, 3,000 feet plus 1,320 feet. Lift. Lift always acts in a direction perpendicular to the relative wind and to the lateral axis of the aircraft. The fact that lift is referenced to the wing, not to the Earth's surface, is the source of many errors in learning flight control. Lift is not always up. Its direction relative to the Earth's surface changes as the pilot maneuvers the aircraft. The magnitude of the force of lift is directly proportional to the density of the air, the area of the wings, and the airspeed. It also depends upon the type of wing and the AOA. Lift increases with an increase in AOA up to the stalling angle, at which point it decreases with any further increase in AOA. In conventional aircraft, lift is therefore controlled by varying the AOA and speed. Pitch/power relationship. An examination of Figure 4.8 illustrates the relationship between pitch and power while controlling flight path and airspeed. In order to maintain a constant lift, as airspeed is reduced, pitch must be increased. The pilot controls pitch through the elevators, which control the AOA. When back pressure is applied on the elevator control, the tail lowers and the nose rises, thus increasing the wing's AOA and lift. Under most conditions, the elevator is placing downward pressure on the tail. This pressure requires energy that is taken from aircraft performance, speed. Therefore, when the CG is closer to the aft portion of the aircraft, the elevator downward forces are less. This results in less energy used for downward forces, in turn resulting in more energy applied to aircraft performance. Thrust is controlled by using the throttle to establish or maintain desired airspeeds. The most precise method of controlling flight path is to use pitch control while simultaneously using power, thrust, to control airspeed. In order to maintain a constant lift, a change in pitch requires a change in power, and vice versa. If the pilot wants the aircraft to accelerate while maintaining altitude, thrust must be increased to overcome drag. As the aircraft speeds up, lift is increased. To prevent gaining altitude, the pitch angle must be lowered to reduce the AOA and maintain altitude. To decelerate while maintaining altitude, thrust must be decreased to less than the value of drag. As the aircraft slows down, lift is reduced. To prevent losing altitude, the pitch angle must be increased in order to increase the AOA and maintain altitude. Drag curves. When induced drag and parasite drag are plotted on a graph, the total drag on the aircraft appears in the form of a drag curve. Graph A of Figure 4.9 shows a curve based on thrust versus drag, which is primarily used for jet aircraft. Graph B of Figure 4.9 is based on power versus drag, and it is used for propeller-driven aircraft. This chapter focuses on power versus drag charts for propeller-driven aircraft. End of page 4 to 6. Understanding the drag curve can provide valuable insight into the various performance parameters and limitations of the aircraft. Because power must equal drag to maintain a steady airspeed, the curve can be either a drag curve or a power required curve. The power required curve represents the amount of power needed to overcome drag in order to maintain a steady speed in level flight. The propellers used on most reciprocating engines achieve peak propeller efficiencies in the range of 80 to 88%. As airspeed increases, the propeller efficiency increases until it reaches its maximum. Any airspeed above this maximum point causes a reduction in propeller efficiency. An engine that produces 160 horsepower will have only about 80% of that power converted into available horsepower, approximately 128 horsepower. The remainder is lost energy. This is the reason the thrust and power available curves change with speed. Regions of command. The drag curve also illustrates the two regions of command, the region of normal command and the region of reversed command. The term region of command refers to the relationship between speed and the power required to maintain or change that speed. Command refers to the input the pilot must give in terms of power or thrust to maintain a new speed once reached. The region of normal command occurs where power must be added to increase speed. This region exists at speeds higher than the minimum drag point primarily as a result of parasite drag. The region of reversed command occurs where additional power is needed to maintain a slower airspeed. This region exists at speeds slower than the minimum drag point, L/D max on the thrust required curve, Figure 4.9, and is primarily due to induced drag. Figure 4.10 shows how one power setting can yield two speeds, points 1 and 2. This is because at point 1 there is high induced drag and low parasite drag, while at point 2 there is high parasite drag and low induced drag. Control characteristics. Most flying is conducted in the region of normal command, for example, cruise, climb, and maneuvers. The region of reversed command may be encountered in the slow-speed phases of flight during takeoff and landing. However, for most general aviation aircraft, this region is very small and is below normal approach speeds. Flight in the region of normal command is characterized by a relatively strong tendency of the aircraft to maintain the trim speed. Flight in the region of reversed command is characterized by a relatively weak tendency of the aircraft to maintain the trim speed. In fact, it is likely the aircraft exhibits no inherent tendency to maintain the trim speed in this area. For this reason, the pilot must give particular attention to precise control of airspeed when operating in the slow-speed phases of the region of reversed command. End of page 4 to 7. Operation in the region of reversed command does not imply that great control difficulty and dangerous conditions exist. However, it does amplify errors of basic flying technique, making proper flying technique and precise control of the aircraft very important. Speed stability, normal command. The characteristics of flight in the region of normal command are illustrated at point A on the curve in Figure 4.11. If the aircraft is established in steady, level flight at point A, lift is equal to weight, and the power available is set equal to the power required. If the airspeed is increased with no changes to the power setting, a power deficiency exists. The aircraft has a natural tendency to return to the initial speed to balance power and drag. If the airspeed is reduced with no changes to the power setting, an excess of power exists. The aircraft has a natural tendency to speed up to regain the balance between power and drag. Keeping the aircraft in proper trim enhances this natural tendency. The static longitudinal stability of the aircraft tends to return the aircraft to the original trimmed condition. An aircraft flying in steady, level flight at point C is in equilibrium. Figure 4.11, if the speed were increased or decreased slightly, the aircraft would tend to remain at that speed. This is because the curve is relatively flat and a slight change in speed does not produce any significant excess or deficiency in power. It has the characteristic of neutral stability, i.e., the aircraft's tendency is to remain at the new speed. Reversed command. The characteristics of flight in the region of reversed command are illustrated at point B on the curve in Figure 4.10. If the aircraft is established in steady, level flight at point B, lift is equal to weight, and the power available is set equal to the power required. When the airspeed is increased greater than point B, an excess of power exists. This causes the aircraft to accelerate to an even higher speed. When the aircraft is slowed to some airspeed lower than point B, a deficiency of power exists. The natural tendency of the aircraft is to continue to slow to an even lower airspeed. This tendency toward instability happens because the variation of excess power to either side of point B magnifies the original change in speed. Although the static longitudinal stability of the aircraft tries to maintain the original trimmed condition, this instability is more of an influence because of the increased induced drag due to the higher AOA in slow-speed flight. Trim. The term trim refers to employing adjustable aerodynamic devices on the aircraft to adjust forces so the pilot does not have to manually hold pressure on the controls. One means is to employ trim tabs. A trim tab is a small, adjustable hinged surface located on the trailing edge of the elevator, aileron, or rudder control surfaces. Some aircraft use adjustable stabilizers instead of trim tabs for pitch trim. Trimming is accomplished by deflecting the tab in the direction opposite to that in which the primary control surface must be held. The force of the airflow striking the tab causes the main control surface to be deflected to a position that corrects the unbalanced condition of the aircraft. Because the trim tabs use airflow to function, trim is a function of speed. Any change in speed results in the need to retrim the aircraft. An aircraft properly trimmed in pitch seeks to return to the original speed before the change. It is very important for instrument pilots to keep the aircraft in constant trim. This reduces the pilot's workload significantly, allowing attention to other duties without compromising aircraft control. Slow-speed flight. Anytime an aircraft is flying near the stalling speed or the region of reversed command, such as in final approach for a normal landing, the initial part of a go-around, or maneuvering in slow flight, it is operating in what is called slow-speed flight. If the aircraft weighs 4,000 pounds, the lift produced by the aircraft must be 4,000 pounds. When lift is less than 4,000 pounds, the aircraft is no longer able to sustain level flight and consequently descends. During intentional descents, this is an important factor and is used in the total control of the aircraft. End of page 4 to 8. However, because lift is required during low-speed flight and is characterized by high AOA, flaps or other high lift devices are needed to either change the camber of the airfoil or delay the boundary level separation. Plain and split flaps, figure 4.12, are most commonly used to change the camber of an airfoil. It should be noted that with the application of flaps, the aircraft will stall at a lower AOA. For example, if the basic wing stalls at 18 degrees without flaps, then with the addition of flaps to the CLmax position, the new AOA that the wing will stall is 15 degrees. However, the value of lift, flaps extended to the CLmax position, produces more lift than lift at 18 degrees on the basic wing. Delaying the boundary layer separation is another way to increase CLmax. Several methods are employed, such as suction and use of a blowing boundary layer control, but the most common device used on general aviation light aircraft is the vortex generator. Small strips of metal placed along the wing, usually in front of the control surfaces, create turbulence. The turbulence in turn mixes high-energy air from outside the boundary layer with boundary layer air. The effect is similar to other boundary layer devices. Figure 4.13, Small airplanes. Most small airplanes maintain a speed well in excess of 1.3 times VSO on an instrument approach. An airplane with a stall speed of 50 knots, VSO, has a normal approach speed of 65 knots. However, the same airplane may maintain 90 knots, 1.8 VSO, while on the final segment of an instrument approach. The landing gear will most likely be extended at the beginning of the descent to the minimum descent altitude, or upon intercepting the glide slope of the instrument landing system. The pilot may also select an intermediate flap setting for this phase of the approach. The airplane at this speed has good positive speed stability, as represented by point A on figure 4.11. Flying in this regime permits the pilot to make slight pitch changes without changing power settings, and accept minor speed changes knowing that when the pitch is returned to the initial setting, the speed returns to the original setting. This reduces the pilot's workload. Aircraft are usually slowed to a normal landing speed when on the final approach just prior to landing. When slowed to 65 knots, 1.3 VSO, the airplane will be close to point C, figure 4.14. At this point, precise control of the pitch and power becomes more crucial for maintaining the correct speed. Pitch and power coordination is necessary because the speed stability is relatively neutral since the speed tends to remain at the new value and not return to the original setting. In addition to the need for more precise airspeed control, the pilot normally changes the aircraft's configuration by extending landing flaps. This configuration change means the pilot must be alert to unwanted pitch changes at a low altitude. End of page 4 to 9. If allowed to slow several knots, the airplane could enter the region of reversed command. At this point, the airplane could develop an unsafe sink rate and continue to lose speed unless the pilot takes a prompt corrective action. Proper pitch and power coordination is critical in this region due to speed instability and the tendency of increased divergence from the desired speed. Large airplanes. Pilots of larger airplanes with higher stall speeds may find the speed they maintain on the instrument approach is near 1.3 VSO, putting them near point C, figure 4.11, the entire time the airplane is on the final approach segment. In this case, precise speed control is necessary throughout the approach. It may be necessary to temporarily select excessive or deficient thrust in relation to the target thrust setting in order to quickly correct for airspeed deviations. For example, a pilot is on an instrument approach at 1.3 VSO, a speed near L/D max, and knows that a certain power setting maintains that speed. The airplane slows several knots below the desired speed because of a slight reduction in the power setting. The pilot increases the power slightly, and the airplane begins to accelerate, but at a slow rate. Because the airplane is still in the flat part of the drag curve, this slight increase in power will not cause a rapid return to the desired speed. The pilot may need to increase the power higher than normally needed to maintain the new speed, allow the airplane to accelerate, then reduce the power to the setting that maintains the desired speed. Climbs. The ability for an aircraft to climb depends upon an excess power or thrust over what it takes to maintain equilibrium. Excess power is the available power over and above that required to maintain horizontal flight at a given speed. Although the terms power and thrust are sometimes used interchangeably, erroneously implying they are synonymous, distinguishing between the two is important when considering climb performance. Work is the product of a force moving through a distance and is usually independent of time. Power implies work rate or units of work per unit of time, and as such is a function of the speed at which the force is developed. Thrust, also a function of work, means the force which imparts a change in the velocity of a mass. During takeoff, the aircraft does not stall even though it may be in a climb near the stall speed. The reason is that excess power, used to produce thrust, is used during this flight regime. Therefore, it is important if an engine fails after takeoff, to compensate the loss of thrust with pitch and airspeed. For a given weight of the aircraft, the angle of climb depends on the difference between thrust and drag, or the excess thrust. When the excess thrust is 0, the inclination of the flight path is 0, and the aircraft is in steady, level flight. When thrust is greater than drag, the excess thrust allows a climb angle depending on the amount of excess thrust. When thrust is less than drag, the deficiency of thrust induces an angle of descent. Acceleration in cruise flight. Aircraft accelerate in level flight because of an excess of power over what is required to maintain a steady speed. This is the same excess power used to climb. Upon reaching the desired altitude with pitch being lowered to maintain that altitude, the excess power now accelerates the aircraft to its cruise speed. However, reducing power too soon after level off results in a longer period of time to accelerate. Turns. Like any moving object, an aircraft requires a sideward force to make it turn. In a normal turn, this force is supplied by banking the aircraft in order to exert lift inward, as well as upward. The force of lift is separated into two components at right angles to each other. Figure 4.14, the upward acting lift together with the opposing weight becomes the vertical lift component. The horizontally acting lift and its opposing centrifugal force are the horizontal lift component, or centripetal force. This horizontal lift component is the sideward force that causes an aircraft to turn. The equal and opposite reaction to this sideward force is centrifugal force, which is merely an apparent force as a result of inertia. End of page 4 to 10. The relationship between the aircraft's speed and bank angle to the rate and radius of turns is important for instrument pilots to understand. The pilot can use this knowledge to properly estimate bank angles needed for certain rates of turn, or to determine how much to lead when intercepting a course. Rate of turn. The rate of turn, normally measured in degrees per second, is based upon a set bank angle at a set speed. If either one of these elements changes, the rate of turn changes. If the aircraft increases its speed without changing the bank angle, the rate of turn decreases. Likewise, if the speed decreases without changing the bank angle, the rate of turn increases. Changing the bank angle without changing speed also causes the rate of turn to change. Increasing the bank angle without changing speed increases the rate of turn, while decreasing the bank angle reduces the rate of turn. The standard rate of turn, 3 degrees per second, is used as the main reference for bank angle. Therefore, the pilot must understand how the angle of bank varies with speed changes, such as slowing down for holding or an instrument approach. Figure 4.15 shows the turn relationship with reference to a constant bank angle or a constant airspeed, and the effects on rate of turn and radius of turn. A rule of thumb for determining the standard rate turn is to divide the airspeed by 10 and add 7. An aircraft with an airspeed of 90 knots takes a bank angle of 16 degrees to maintain a standard rate turn. 90 divided by 10 plus 7 equals 16 degrees. Radius of turn. The radius of turn varies with changes in either speed or bank. If the speed is increased without changing the bank angle, the radius of turn increases, and vice versa. If the speed is constant, increasing the bank angle reduces the radius of turn, while decreasing the bank angle increases the radius of turn. This means that intercepting a course at a higher speed requires more distance, and therefore, requires a longer lead. If the speed is slowed considerably in preparation for holding or an approach, a shorter lead is needed than that required for cruise flight. Coordination of rudder and aileron controls. Anytime ailerons are used, adverse yaw is produced. Adverse yaw is caused when the ailerons are deflected as a roll motion, as in turn, is initiated. In a right turn, the right aileron is deflected upward while the left is deflected downward. Lift is increased on the left side and reduced on the right, resulting in a bank to the right. However, as a result of producing lift on the left, induced drag is also increased on the left side. The drag causes the left wing to slow down, in turn causing the nose of the aircraft to initially move left in the direction opposite of the turn. Correcting for this yaw with rudder when entering and exiting turns is necessary for precise control of the airplane when flying on instruments. The pilot can tell if the turn is coordinated by checking the ball and the turn and slip indicator or the turn coordinator. Figure 4.16, as the aircraft banks to enter a turn, a portion of the wing's vertical lift becomes the horizontal component. Therefore, without an increase in back pressure, the aircraft loses altitude during the turn. The loss of vertical lift can be offset by increasing the pitch in 1/2 bar width increments. Trim may be used to relieve the control pressures, however, if used, it has to be removed once the turn is complete. In a slipping turn, the aircraft is not turning at the rate appropriate to the bank being used, and the aircraft falls to the inside of the turn. The aircraft is banked too much for the rate of turn, so the horizontal lift component is greater than the centrifugal force. A skidding turn results from excess of centrifugal force over the horizontal lift component, pulling the aircraft toward the outside of the turn. The rate of turn is too great for the angle of bank, so the horizontal lift component is less than the centrifugal force. End of page 4 to 11. An inclinometer, located in the turn coordinator, or turn and bank indicator, indicates the quality of the turn, and should be centered when the wings are banked. If the ball is off of center on the side toward the turn, the aircraft is slipping and rudder pressure should be added on that side to increase the rate of turn, or the bank angle should be reduced. If the ball is off of center on the side away from the turn, the aircraft is skidding and rudder pressure toward the turn should be relaxed, or the bank angle should be increased. If the aircraft is properly rigged, the ball should be in the center when the wings are level. Use rudder and/or aileron trim if available. The increase in induced drag, caused by the increase in AOA necessary to maintain altitude, results in a minor loss of airspeed if the power setting is not changed. Load factor. Any force applied to an aircraft to deflect its flight from a straight line produces a stress on its structure. The amount of this force is termed load factor. A load factor is the ratio of the aerodynamic force on the aircraft to the gross weight of the aircraft, e.g., lift/weight. For example, a load factor of 3 means the total load on an aircraft's structure is 3 times its gross weight. When designing an aircraft, it is necessary to determine the highest load factors that can be expected in normal operation under various operational situations. These highest load factors are called limit load factors. Aircraft are placed in various categories, i.e., normal, utility, and acrobatic, depending upon the load factors they are designed to take. For reasons of safety, the aircraft must be designed to withstand certain maximum load factors without any structural damage. End of page 4 to 12. The specified load may be expected in terms of aerodynamic forces, as in turns. In level flight in undisturbed air, the wings are supporting not only the weight of the aircraft, but centrifugal force as well. As the bank steepens, the horizontal lift component increases, centrifugal force increases, and the load factor increases. If the load factor becomes so great that an increase in AOA cannot provide enough lift to support the load, the wing stalls. Since the stalling speed increases directly with the square root of the load factor, the pilot should be aware of the flight conditions during which the load factor can become critical. Steep turns at slow airspeed, structural ice accumulation, and vertical gusts in turbulent air can increase the load factor to a critical level. Icing. One of the greatest hazards to flight is aircraft icing. The instrument pilot must be aware of the conditions conducive to aircraft icing. These conditions include the types of icing, the effects of icing on aircraft control and performance, effects of icing on aircraft systems, and the use and limitations of aircraft de-ice and anti-ice equipment. Coping with the hazards of icing begins with pre-flight planning to determine where icing may occur during a flight and ensuring the aircraft is free of ice and frost prior to takeoff. This attention to detail extends to managing de-ice and anti-ice systems properly during the flight, because weather conditions may change rapidly, and the pilot must be able to recognize when a change of flight plan is required. Types of icing. Structural icing. Structural icing refers to the accumulation of ice on the exterior of the aircraft. Ice forms on aircraft structures and surfaces when supercooled droplets impinge on them and freeze. Small and/or narrow objects are the best collectors of droplets and ice up most rapidly. This is why a small protuberance within sight of the pilot can be used as an ice evidence probe. It is generally one of the first parts of the airplane on which an appreciable amount of ice forms. An aircraft's tailplane is a better collector than its wings, because the tailplane presents a thinner surface to the airstream. Induction icing. Ice in the induction system can reduce the amount of air available for combustion. The most common example of reciprocating engine induction icing is carburetor ice. Most pilots are familiar with this phenomenon, which occurs when moist air passes through a carburetor venturi and is cooled. As a result of this process, ice may form on the venturi walls and throttle plate, restricting airflow to the engine. This may occur at temperatures between 20 degrees Fahrenheit -7 degrees Celsius and 70 degrees Fahrenheit 21 degrees Celsius. The problem is remedied by applying carburetor heat, which uses the engine's own exhaust as a heat source to melt the ice or prevent its formation. On the other hand, fuel-injected aircraft engines usually are less vulnerable to icing but still can be affected if the engine's air source becomes blocked with ice. Manufacturers provide an alternate air source that may be selected in case the normal system malfunctions. In turbojet aircraft, air that is drawn into the engines creates an area of reduced pressure at the inlet, which lowers the temperature below that of the surrounding air. In marginal icing conditions, i.e., conditions where icing is possible, this reduction in temperature may be sufficient to cause ice to form on the engine inlet, disrupting the airflow into the engine. Another hazard occurs when ice breaks off and is ingested into a running engine, which can cause damage to fan blades, engine compressor stall, or combustor flameout. When anti-icing systems are used, run-back water also can refreeze on unprotected surfaces of the inlet and, if excessive, reduce airflow into the engine or distort the airflow pattern in such a manner as to cause compressor or fan blades to vibrate, possibly damaging the engine. Another problem in turbine engines is the icing of engine probes used to set power levels, for example, engine inlet temperature or engine pressure ratio (EPR) probes, which can lead to erroneous readings of engine instrumentation operational difficulties or total power loss. The type of ice that forms can be classified as clear, rime, or mixed, based on the structure and appearance of the ice. The type of ice that forms varies depending on the atmospheric and flight conditions in which it forms. Significant structural icing on an aircraft can cause serious aircraft control and performance problems. Clear ice. A glossy, transparent ice formed by the relatively slow freezing of super-cooled water is referred to as clear ice. Figure 4.17, the terms clear and glaze have been used for essentially the same type of ice accretion. This type of ice is denser, harder, and sometimes more transparent than rime ice. With larger accretions, clear ice may form horns. Figure 4.18, temperatures close to the freezing point, large amounts of liquid water, high aircraft velocities, and large droplets are conducive to the formation of clear ice. End of page 4-13. Rime ice. A rough, milky, opaque ice formed by the instantaneous or very rapid freezing of super-cooled droplets as they strike the aircraft is known as rime ice. Figure 4.19, the rapid freezing results in the formation of air pockets in the ice, giving it an opaque appearance and making it porous and brittle. For larger accretions, rime ice may form a streamlined extension of the wing. Low temperatures, lesser amounts of liquid water, low velocities, and small droplets are conducive to the formation of rime ice. Mixed ice. Mixed ice is a combination of clear and rime ice formed on the same surface. It is the shape and roughness of the ice that is most important from an aerodynamic point of view. General effects of icing on airfoils. The most hazardous aspect of structural icing is its aerodynamic effects. Figure 4.20, ice alters the shape of an airfoil, reducing the maximum coefficient of lift and AOA at which the aircraft stalls. Note that at very low AOAs, there may be little or no effect of the ice on the coefficient of lift. Therefore, when cruising at a low AOA, ice on the wing may have little effect on the lift. However, note that the ice significantly reduces the CLmax, and the AOA at which it occurs, the stall angle, is much lower. Thus, when slowing down and increasing the AOA for approach, the pilot may find that ice on the wing, which had little effect on lift in cruise now, causes stall to occur at a lower AOA and higher speed. Even a thin layer of ice at the leading edge of a wing, especially if it is rough, can have a significant effect in increasing stall speed. For large ice shapes, especially those with horns, the lift may also be reduced at a lower AOA. The accumulation of ice affects the coefficient of drag of the airfoil. Figure 4.20, note that the effect is significant even at very small AOAs. End of page 4 to 14. A significant reduction in CLmax and a reduction in the AOA where stall occurs can result from a relatively small ice accretion. A reduction of CLmax by 30% is not unusual, and a large horn ice accretion can result in reductions of 40% to 50%. Drag tends to increase steadily as ice accretes. An airfoil drag increase of 100% is not unusual, and for large horn ice accretions, the increase can be 200% or even higher. Ice on an airfoil can have other effects not depicted in these curves. Even before airfoil stall, there can be changes in the pressure over the airfoil that may affect a control surface at the trailing edge. Furthermore, on takeoff, approach, and landing, the wings of many aircraft are multi-element airfoils with 3 or more elements. Ice may affect the different elements in different ways. Ice may also affect the way in which the airstreams interact over the elements. Ice can partially block or limit control surfaces, which limits or makes control movements ineffective. Also, if the extra weight caused by ice accumulation is too great, the aircraft may not be able to become airborne, and if in flight, the aircraft may not be able to maintain altitude. Therefore, any accumulation of ice or frost should be removed before attempting flight. Another hazard of structural icing is the possible uncommanded and uncontrolled roll phenomenon, referred to as roll upset, associated with severe in-flight icing. Pilots flying aircraft certificated for flight in known icing conditions should be aware that severe icing is a condition outside of the aircraft's certification icing envelope. Roll upset may be caused by airflow separation, aerodynamic stall, which induces self-deflection of the ailerons and loss of or degraded roll handling characteristics, figure 4.21. These phenomena can result from severe icing conditions without the usual symptoms of ice accumulation or a perceived aerodynamic stall. Most aircraft have a nose-down pitching moment from the wings because the CG is ahead of the CP. It is the role of the tailplane to counteract this moment by providing a downward force. Figure 4.22, the result of this configuration is that actions which move the wing away from stall, such as deployment of flaps or increasing speed, may increase the negative AOA of the tail. With ice on the tailplane, it may stall after full or partial deployment of flaps. Figure 4.23, since the tailplane is ordinarily thinner than the wing, it is a more efficient collector of ice. On most aircraft, the tailplane is not visible to the pilot, who therefore cannot observe how well it has been cleared of ice by any de-icing system. Thus, it is important that the pilot be alert to the possibility of tailplane stall, particularly on approach and landing. End of page 4 to 15. Piper PA-34-200T, Des Moines, Iowa. The pilot of this flight, which took place on January 9, 1996, said that upon crossing the runway threshold and lowering the flaps 25 degrees, the airplane pitched down. The pilot immediately released the flaps and added power, but the airplane was basically uncontrollable at this point. The pilot reduced power and lowered the flaps before striking the runway on its centerline and sliding 1,000 feet before coming to a stop. The accident resulted in serious injury to the pilot, the sole occupant. Examination of the wreckage revealed heavy impact damage to the airplane's forward fuselage, engines, and wings. Approximately 1/2 inch of rime ice was observed adhering to the leading edges of the left and right horizontal stabilizers and along the leading edge of the vertical stabilizer. The National Transportation Safety Board, NTSB, determined the probable cause of the accident was the pilot's failure to use the airplane's de-icing system, which resulted in an accumulation of empennage ice and a tailplane stall. Factors relating to this accident were the icing conditions and the pilot's intentional flight into those known conditions. Tailplane stall symptoms. Any of the following symptoms, occurring singly or in combination, may be a warning of tailplane icing. 1. Elevator control pulsing, oscillations, or vibrations. 2. Abnormal nose-down trim change. 3. Any other unusual or abnormal pitch anomalies, possibly resulting in pilot-induced oscillations. 4. Reduction or loss of elevator effectiveness. 5. Sudden change in elevator force. Control would move nose-down if unrestrained. And 6. Sudden uncommanded nose-down pitch. If any of the above symptoms occur, the pilot should 7. Immediately retract the flaps to the previous setting and apply appropriate nose-up elevator pressure. 8. Increase airspeed appropriately for the reduced flap extension setting. 9. Apply sufficient power for aircraft configuration and conditions. High engine power settings may adversely impact response to tailplane stall conditions at high airspeed in some aircraft designs. Observe the manufacturer's recommendations regarding power settings. 10. Make nose-down pitch changes slowly, even in gusting conditions, if circumstances allow. And 11. If a pneumatic de-icing system is used, operate the system several times in an attempt to clear the tailplane of ice. Once a tailplane stall is encountered, the stall condition tends to worsen with increased airspeed and possibly may worsen with increased power settings at the same flap setting. Airspeed, at any flap setting, in excess of the airplane manufacturer's recommendations, accompanied by uncleared ice contaminating the tailplane, may result in a tailplane stall and uncommanded pitch down from which recovery may not be possible. A tailplane stall may occur at speeds less than the maximum flap extended speed, VFE. Propeller icing. Ice buildup on propeller blades reduces thrust for the same aerodynamic reasons that wings tend to lose lift and increase drag when ice accumulates on them. The greatest quantity of ice normally collects on the spinner and inner radius of the propeller. Propeller areas on which ice may accumulate and be ingested into the engine normally are anti-iced rather than de-iced to reduce the probability of ice being shed into the engine. Effects of icing on critical aircraft systems. In addition to the hazards of structural and induction icing, the pilot must be aware of other aircraft systems susceptible to icing. The effects of icing do not produce the performance loss of structural icing or the power loss of induction icing but can present serious problems to the instrument pilot. Examples of such systems are flight instruments, stall warning systems, and windshields. Flight instruments. Various aircraft instruments, including the airspeed indicator, altimeter, and rate of climb indicator, utilize pressures sensed by pitot tubes and static ports for normal operation. End of page 4 to 16. When covered by ice, these instruments display incorrect information, thereby presenting serious hazard to instrument flight. Detailed information on the operation of these instruments and the specific effects of icing is presented in Chapter 5, Flight Instruments. Stall warning systems. Stall warning systems provide essential information to pilots. These systems range from a sophisticated stall warning vane to a simple stall warning switch. Icing affects these systems in several ways, resulting in possible loss of stall warning to the pilot. The loss of these systems can exacerbate an already hazardous situation. Even when an aircraft's stall warning system remains operational during icing conditions, it may be ineffective because the wing stalls at a lower AOA due to ice on the airfoil. Windshields. Accumulation of ice on flight deck windows can severely restrict the pilot's visibility outside of the aircraft. Aircraft equipped for flight into known icing conditions typically have some form of windshield anti-icing to enable the pilot to see outside the aircraft in case icing is encountered in flight. One system consists of an electrically heated plate installed onto the airplane's windshield to give the pilot a narrow band of clear visibility. Another system uses a bar at the lower end of the windshield to spray de-icing fluid onto it and prevent ice from forming. On high-performance aircraft that require complex windshields to protect against bird strikes and withstand pressurization loads, the heating element often is a layer of conductive film or thin wire strands through which electric current is run to heat the windshield and prevent ice from forming. Antenna icing. Because of their small size and shape, antennas that do not lay flush with the aircraft's skin tend to accumulate ice rapidly. Furthermore, they often are devoid of internal anti-icing or de-icing capability for protection. During flight in icing conditions, ice accumulations on an antenna may cause it to begin to vibrate or cause radio signals to become distorted, and it may cause damage to the antenna. If a frozen antenna breaks off, it can damage other areas of the aircraft in addition to causing a communication or navigation system failure. Summary: ice-contaminated aircraft have been involved in many accidents. Takeoff accidents have usually been due to failure to de-ice or anti-ice critical surfaces properly on the ground. Proper de-icing and anti-icing procedures are addressed in two other pilot guides: Advisory Circular, AC 120-58, Pilot Guide, Large Aircraft Ground De-icing, and AC 135-17, Pilot Guide, Small Aircraft Ground De-icing. The pilot of an aircraft, which is not certificated or equipped for flight in icing conditions, should avoid all icing conditions. The aforementioned guides provide direction on how to do this, and on how to exit icing conditions promptly and safely should they be inadvertently encountered. The pilot of an aircraft, which is certificated for flight in icing conditions, can safely operate in the conditions for which the aircraft was evaluated during the certification process, but should never become complacent about icing. Even short encounters with small amounts of rough icing can be very hazardous. The pilot should be familiar with all information in the Aircraft Flight Manual, AFM, or Pilot's Operating Handbook, POH, concerning flight in icing conditions and follow it carefully. Of particular importance are proper operation of ice protection systems and any airspeed minimums to be observed during or after flight in icing conditions. There are some icing conditions for which no aircraft is evaluated in the certification process, such as supercooled large drops, SLD. These sub-freezing water droplets, with diameters greater than 50 microns, occur within or below clouds, and sustained flight in these conditions can be very hazardous. The pilot should be familiar with any information in the AFM or POH relating to these conditions, including aircraft-specific cues for recognizing these hazardous conditions within clouds. The information in this chapter is an overview of the hazards of aircraft icing. For more detailed information, refer to AC 91-74, Pilot Guide, Flight in Icing Conditions, AC 91-51, Effective Icing on Aircraft Control and Airplane De-ice and Anti-Ice Systems, AC 20-73, Aircraft Ice Protection, and AC 23.143-1, Ice Contaminated Tailplane Stall, ICTS.